Welcome back to ECE 441A 541A. If I hope this doesn't come as a surprise, but Friday your lab is due, lab number 2. All of that is based on this assumption that your model from lab number 1 is correct, but you might see based on your performance or response that you're getting after controlling your system that maybe it's not quite what you thought it was initially, but you also have to realize that the system that you are producing with your model is an ideal two-pole linear system, and we have some nonlinear behavior or some friction in there that may not be being modeled by our plant. But look at that and try to achieve what's asked of you in lab number 2, and if you get some differences, that's maybe all the better. Then that sort of makes you dig in and try to understand, what is my system really doing, or do I have a better way of modeling it? Homework 6 will be due the next Friday, and on that day we won't be meeting in class. That's engineer's breakfast, so class is canceled a week from Friday. That's what I'm meaning by no class. Exam 3 is a couple of Fridays after that, just for your bookkeeping purposes. Today what I want to do is introduce the 2 conditions behind the root locus. All of these rules for sketching the root locus will come about from basically understanding complex numbers. Knowing how to rewrite a complex number as a magnitude and an angle. And that will then determine these rules that we are going to start discussing, and I've simply listed those so that we can start to embed those in this process of sketching. And I've tried to do it fairly briefly in terms of these descriptions of the rules, and you will learn that maybe you can't just march down rule 1, rule 2, rule 3. You may have to sort of have these floating in your head, and in some cases some of these rules may or may not be applicable to the system that you are trying to sketch the closed loop behavior for. Remember what we're trying to do, and we'll talk about that in just a minute. But we have boiled this process down of sketching a root locus into 6 rules or ways of trying to make these sketches. Where do we start and where do we end as far as these branches of the root locus? That's the first rule. What segments of the root locus actually live on the real line or on the real axis? Sometimes they may not be, maybe there may be no real line segments that are on the root locus, but that's rule 2. We'll then figure out how to draw guidelines or asymptotes that allow us to determine where are these branches going to go to eventually as we crank up the gain K to large values. We're sketching asymptotes, and we want to know, how do these branches of our root locus approach those asymptotes as K gets bigger? These will all hopefully make a little bit more sense as we go through them. We'll have breakaway and reentry points on the real axis. If we do have segments of our root locus on the real line, we may have to come into the real line, or we may have to break away from the real line. That's what rule number 4 does. Do any of these branches go across the imaginary axis? That's rule number 5, the imaginary axis crossing. And the last one is the fun one. How do we arrive or depart from complex poles or complex zeros? If we have complex pole pairs, how does the root locus leave those? And in particular, at what angle do we depart those poles? If we have complex zeros, how do we actually arrive? At what angle do we come in, or do we approach those complex zeros? Let's just quickly sort of set the stage for this process. I think all of this we have talked about, but we are going to typically say we have Nevada poles, n, little n. We're just going to say little n is going to be how many poles we have in our system. And the open loop poles refer to how many poles we have in our plant, G, how many poles we have in our controller, G sub C, and how many poles we have in maybe the feedback path, which we are labeling H. And we want to know, how do the closed loop poles migrate around in the S-plane? And it's a nice pattern. It's not like they randomly just jump around. These closed loop poles migrate or move or have a locus to them, and we want to know, how do they move around as we adjust this single parameter, and here we're labeling it as K, as we let K go from 0 to infinity. We will typically use negative feedback, but sometimes your system may be set up so that you have an effective positive feedback loop, and then actually the rules change completely, or they change sign, obviously, but there's a sign change, and that changes some of the rules. And I want you to just be aware of that. If you end up with a positive feedback system that produces some characteristic equation, and you're going, this doesn't look like the root locus I'm used to thinking about. Well, that's because somebody's flipped the sign on you, and that's now modified these 6 rules that we are going to be developing based on negative feedback. If we have a negative feedback system or a positive feedback system, we can produce this closed loop transfer function, kg over 1 plus kgh, and I've tried to color code this. If you have negative feedback, that's 1 plus kgh. If you actually had positive feedback, you would have a 1 minus kgh in the denominator. And we are interested in this denominator expression, 1 plus kgh, set that equal to 0, and we want to know what values of s satisfy that equation as we adjust k from 0 up to infinity. We want to know, how do the roots of this expression, or of this characteristic equation, how do they move as we manipulate, or let's say turn that knob on k from 0 all the way to infinity. That's what we're trying to develop now, today, is how do we actually sketch those? And that's where these rules are coming from. And we are actually going to focus on the red piece, the negative feedback, to derive these 6 rules. If you had the other case, positive feedback, these rules would be modified slightly. What's the characteristic equation when we have negative feedback? In terms of, and here, notice what I'm doing in this block diagram. I'm now collecting the plant and the controller together and calling that forward branch. All of that together, I will typically just say that's my G of S, capital G of S. And it may be a mixture of the plant and the controller's poles and zeros. But I'm just going to call that whole mess G. If this is what I'm calling that dashed piece, capital G, then what's my characteristic equation for the closed loop system in negative feedback? And it's right there on the screen, isn't it? It's the one with the red. It's now this 1 plus K G of S, H of S, equaling 0. This is what we want to understand. We want to know what values of S satisfy this equation as we adjust k from 0 to infinity. If somebody put in a k of 1/2, you could solve this for S and find the roots of this equation. But we could also write this another way. We could now solve this or subtract 1 from both sides. And that's another way of writing that same equation. Just k g of s h of s is equal to -1. And here's one of the ways that we will modify -1 to help us make these sketches. We are going to write -1 as a magnitude of 1 and as an angle. What's the angle? There's my complex S-plane. I'm now saying here I am at -1. I move over there a distance of 1. That has a length of 1. The magnitude to that point, I pull out my string, and that string is now 1 unit long. I can now take that string, tie one end to the origin and put the other end, and it ends up at -1. But if I'm now referencing that point to the positive real axis, what's the angle of that line segment? I heard two answers. They're both right. It could be 180. You could go this way, or you could have gone this way. And they're both equally valid. What we will do, I will typically go ahead and go this way because a lot of times we'll be thinking of these angles as introducing delay, and we always have sort of a negative delay. So I'm going to just go ahead and agree that we'll get to that point, -1, by a magnitude or a length of 1, and we'll travel in the -180 direction. So you could get there going 1 at 180, but we're just agreeing that we will say -1 is now 1 at an angle of -180. And all the points S that satisfy that equation will produce our root locus. And in fact, that right-hand side has two parts, doesn't it? It has a magnitude piece and a phase piece. And those are our two conditions that we will use to sketch our root locus. The points on the root locus must satisfy those two conditions. So if you get lost in these rules, just realize that it's not that big of a deal. They all are just saying we have two conditions, one at an angle of -180. And I will refer to those when I talk about this in developing these rules, or even when we start getting into the design piece of this process, which is after learning how to make the sketches. We have a magnitude condition, which says that we need the magnitude of the left-hand side to equal the magnitude on the right-hand side. We're now saying the magnitude condition is we have this product of k, g of s, h of s equaling 1. If you plug in any value of s, any complex value of s, into that expression, k, g of s, h of s, it's going to be a complex number. You can find its magnitude. We're saying that this combination of k with g and h we're looking for the values of s that make that true. The other condition we will just call the phase condition, or I may call it the phase angle condition. And this one now says that we need the angle of that left-hand side to be equal to the angle on the right-hand side. And the angle on the right-hand side is minus 180. The phase condition then says that the angle of K, G of S, H of S is equal to minus 180 degrees. And all of these rules that we are developing for the root locus, all root locus rules arise from both of those, or either of those two conditions, or the combination. All root locus rules arise from these two conditions: the magnitude condition and the phase condition. So if we now have this expression, 1 plus k g of s h of s equaling 0, that's our characteristic equation, we will usually put that into a, let's say, a standard notation which is simply to agree that all of the numerator factors in g and h will just lump into one numerator polynomial, n of s, and everything that's in the denominator of g of s and h of s, we're just going to lump all of those factors into a new, just to simplify our terminology or notation. And we will call this piece the open loop piece. So n of s, if we say, what are our open loop zeros? Now I'm wanting you to say, oh, what are the values of s that cause this little n of s to be 0? What are the poles, open loop poles in this root locus argument? After we've put everything into a standard form, it will boil down to this, and then you would be answering me with, oh, the roots of d of s are your open loop poles. And the very first thing that we do is, in this root locus process, is we start actually with rule number 1. That's nice. We start with rule number 1. But we may mix and match some of these rules, but for now we can actually agree that everything starts with rule number 1. Here are our root locus construction rules. And I forgot to put it on D2L to bring your hard hats today, but we are going to be doing some construction. Hopefully everyone has closed-toed shoes if you're doing your labs, which your labs are due on Friday. Just a reminder. It's getting a little bit cooler, so maybe you don't have as many chances for wearing open-toed shoes. So you don't have to go home, to do the lab. Rule 1. This deals with where we start the root locus diagram, or these branches, and where we end. And I'm just labeling rule 1 as the starting and ending points, and in particular, we've agreed to start when k is equal to 0, and we're turning up that knob all the way up to when k goes to a very large value, infinite. Here's rule 1. We actually, the root loci branches start, and this is when the gain k is equal to 0, on the open loop poles, and remember what those were, we've agreed that that's what we will call the roots of the denominator polynomial that includes all of the denominator pieces from g and h. So the roots of d of s are our open loop poles. That's where our root locus branches start. And then I'm going to say, and sum of the branches end, and that's when k is approaching infinity. Sum of the branches end on the open loop zeros. And we've agreed that the open loop zeros are the roots of that numerator expression that comes from all of our possible zero factors in g and h. That's rule number one, and I qualified that I said sum. That's a really precise term, isn't it? Sum. But in fact, it is fairly precise in this process. Sum actually means, anybody have an idea? We have how many root locus branches to begin with? Maybe I didn't. I said it somewhere. We're agreeing that we have Nevada poles. So we're assuming that d of s starts with n, let's say 10 roots. So let's say n of s was a 10th order polynomial. I'm sorry, d of s was a 10th order polynomial, then little n, that's kind of confusing, isn't it? We have n and n of s, and they're not related. They're not even cousins. Sorry. But d of s has a power or an order of little n, 10. And we actually may make that a little bit more precise. We may start calling that p for the number of poles and z for the number of zeros. Here, this sum actually refers to the number of finite zeros, which are actually the finite roots of little n of s. Now, where does this rule come from? We have our starting characteristic equation, and we are looking for the values of s that make this true. And that's kind of messy if we keep the 1 and the n and the d as a ratio. So let's get everything over a common denominator. And then we have d of s plus k n of s, and that's the same equation. And what we are doing, we want that to equal 0. That means we're focusing on what values of s satisfy that numerator expression in this characteristic equation. D of s plus k n of s equal to 0. Now, as k is small, how small are we making k? Where do we begin? 0. If k is equal to 0, what values of s cause that equation to be true? The roots of d of s. Those were our agreed on open loop poles. So we're starting our diagrams at the x's, at our open loop poles. When k gets really, really big, what are the roots of that going to be, of that expression? If k gets really, really big, what's k n of s look like relative to d of s? Does one sort of dominate the other if k is big? Yes, the k n of s starts to dominate, and so we're now approaching in the solution to this, we're approaching the zeros of little n of s. That's where we're finishing some of these branches. Let's look at an example. Let's say now that we have a g of s of s plus 1 and s plus 2 and s plus 3. I spent hours trying to come up with a transfer function. 1, 2, 3. Yes? Yes. So the question was, we are now examining that expression, d plus kn, and we're setting it equal to 0, and we're trying to find the values of s that make that happen. And we are going to adjust k, so we'll pick k equal to 1, and then solve that equation. We'll set k equal to 2. We're not doing that, we're virtually doing that. We'll set k equal to 2 and solve that equation. Now as we set k equal to 10 billion, which piece of that dominates or has the most impact? Well, it would be the n of s factor. And that would then cause everything to equal 0, effectively, is sort of the intuitive way of thinking of it. Don't spend too much time confusing yourself on that. We start on the open loop poles and we end on the open loop zeros, the finite open loop zeros. Let's say g of s is 1, 2, 3, and h of s I'm sure you guessed that structure, didn't you? Is s plus 7 over s plus 5. These were just, after 3 or 4 hours of study, these appeared. Okay? No. Here's a transfer function, or two transfer functions. We now will refer to these or label these now as we are the open loop zeros we will indicate by an open 0, and the open loop poles will be x's. If that's how we sketch these, and now we have this S-plane, here's the real axis, here's the imaginary axis. Maybe I shouldn't put tails on those, but I'll do a different color. Here's -1, -3, -5, -7, and now we need to put down x's and o's. Let's put the o's down first. Where do they belong? Where are my o's? I hear a 1. Do we want to qualify that 1? We now are looking for the values of s that satisfy, yes. So we want s to be -1, don't we? That's probably what you meant, because I was drawing only negative numbers. But -1 for s will cause that numerator to vanish. So we can put a 0 right there. What do I want to, let me put a 0 right there. Do we have any other finite zeros? -7. Those are our two zeros. We had two finite zeros. Our poles are at -2, -3, our open loop poles, as we've agreed to call them, -2, -3, and -5. There is our pole 0 diagram, and that's the very first step in this root locus construction. That's pretty straightforward. Now what we want to do is identify Well, on this diagram, how many ways have we sliced and diced? How many ways, how many segments have we identified on the real line by this placement of X's and O's? How many line segments are there? In general, just how many line segments? I'm not talking about root locus. Just if I had to, if this was a loaf of bread on the line, this was a French loaf of bread on the real line, and now I'm cutting it up. And everywhere I'm slicing it at either a zero, a finite zero, or a pole. Now, how many pieces of bread would I have to share? That's all I'm saying. Do I have more than fit on my hand? Great question. The question was, how long is this loaf of French bread? Does it extend beyond the two ends? And the answer is yes. That's a very good question. My loaf of bread is infinitely long. Okay? So now, how many pieces? So if you're lucky, you get one of those end pieces, right? If you're hungry. That may or may not be good. You like my metaphor here, French bread and cutting it up? I don't know where that came from. Well, it's always going to be food if it's me, right? So how many pieces of French bread did we end up with? How many line segments have we identified? 6. Are we good with that? Now what we want to know is, of those 6 pieces, of those 6 line segments on the real line, how many actually belong to the root locus? Those are the ones that we want to shade. That's rule number 2. So rule number 2 deals with, what color was I using for rules? Oh, okay. Rule 2 is referring to the root loci segments that are on the real axis. And here is the way that we will determine which of those pieces of French bread are going to be shaded. We will say a line segment on the real axis. And how many did we have for this example? How many line segments? You told me 6, so don't change your answer now. We have 6 line segments that we've now identified. A line segment, one of those 6 pieces, a line segment on the real axis is a part of the root locus if and only if an odd number, this means odd in a numerical sense, 1, 3, 5, not strange. So this is odd, an odd number of poles and or zeros. So it's the combination of poles and zeros. You count up those, and if it's odd, if it's an odd number, if the odd number of poles and zeros lie to the right, of the line segment. And this actually all depends in terms of justification for where in the world did this come from. This comes from the phase angle. What? Phase angle segment. Phase angle condition. All right, it may not be clear yet. That may be very wordy. But now we look at this real line and we start moving along these 6 different segments, and we look to our right and we say, do I see an odd number of poles and zeros to my right? And if I do, then I shade that line segment. With that thinking, let's go back here and see if we can identify which of those 6 line segments that we've now separated our real line into belong to the root locus. If I am now standing at +2, I'm on that really long piece of French bread, aren't I? From -1 all the way up to +infinity. That's a big segment. I'm standing now at +2 and I look to my right. Do I see any poles and zeros? No, so they can't be odd, can it? That can't belong to the root locus. Now I step over and I go to maybe -1.5. And I'm now at -1.5, right there, and I say, I'm looking to my right. Better do this with you, or I'll get confused. And now I look and I say, do I see poles and zeros to my right? And the answer is, yes, you see poles and zeros. How many? 1. Is 1 odd? Yes. So now we know that anywhere we stand here actually is going to see that 1 odd pole or zero, and that segment is going to belong to the root locus. Now what we've said is our phase angle condition says that this transfer function g of s, h of s has to have an angle of -180 degrees. If you look at g of s and h of s as a complex number, you could find that complex number by first looking at the magnitude and phase of s plus 1, then looking at the magnitude and phase of s plus 2 and s plus 3, and you would then algebraically add those angles up, and you would multiply and divide to get the magnitude. We're just interested in the angle. If I now look at the angle contributed by that 0, what's it contributing at this point? If I said, I'm right there and I want to know that 0, what's the angle of that 0? It's -180, because I have to actually look around and go that far to get to that point. I have to turn 180 degrees to get to that point. What are my angles from all these other poles and zeros to the left? I don't have to move, do I? I just have to look straight or at a flat angle. Nothing. 0 degrees, 0 degrees, 0 degrees, and 0 degrees. The sum of those phases, -180. So that satisfies the phase condition. All right, is that sort of clear? What if we go here to -2.5 or -2.2? Do I have poles and zeros to the right of that point? Yes. How many? 2. Doesn't matter if they're a pole or a zero, you just count the number. It's 2. 2 is not odd, is it? So any point in between -2 and -3 in that piece of French bread is not on the root locus. Is that making sense? And if you look, the 0 will contribute -180. The pole at -2 will contribute -180, and all the others are contributing 0. The net effect is -360 or 0. That's not -180. So that can't be. Any point between -2 and -3 cannot live on the root locus. What about this point here? -3.8. or minus 4, or minus 4.5. It's all going to see the same number of poles and zeros to the right. Is that clear? And it's odd, so this segment belongs to the root locus. What about the segment between minus 5 and minus 7? No, there's an even number of poles and zeros to the right. And finally, this infinitely long piece is a part of the root locus. From minus 7 all the way to minus infinity, that belongs to the root locus. Questions on that? That's Rule 2. Let's look at another example for Rule 2. And you always wondered why you studied even and odd numbers in mathematics. Now you know it's so you can sketch root loci. Rule number 2, S-plane. Now I'm changing up the plant. Suppose that I now have a plant that has a pole there, a zero there, a pole here, a pole here, a pole here, a zero here, a zero at its conjugate, and a pole there. And now I want to know from rule number 2 which segments along the real line belong to the root locus. And the first question you might ask is, how many pieces of French bread do I have? How many line segments exist? How many? And these line segments could be really long. If you're lucky, you get that piece, right? If you're sitting around a table and you've now cut the piece of French bread into parts, how many pieces do you have, or segments? 5. Which segments belong to the root locus? From 0 to plus infinity, are there poles and zeros to the right? No, so that can't be on the root locus. What about between 0 and, I don't know, minus 1? Let's say that 0 is at minus 1. Is this segment of the real axis a part of the root locus? I knew that was going to happen. Deep breath. So I can't make my root locus too prominent, or it will disappear. So I start scratching, it thinks I'm trying to erase, and it just erases. Your paper won't do that, I hope. Not on the exam. But Dr. Tharp, I had it all written, and it just disappeared. Give me 100, please. I had it all right there. It was just like your solutions. It was. Something happened. More than just the dog ate it, huh? Because we don't allow dogs on the exam. Where were we? Between minus 1 and let's say minus 3, is that line segment a part of the root locus? Yes or no? Up or down? Up is yes, down is no. Thumbs. No. Pardon? What's minus 3? I don't know what minus 3 is. Just humor me. There, how's that? Okay, no. Let's say this is now minus 7. How about between minus 3 and minus 7? Thumbs? How about between minus 7 and minus infinity? No. Okay, you got this rule down, right? It doesn't matter what's happening with poles and zeros off the real line. You just focus on the number of poles and zeros that are to the right on the real line. Don't worry, because their angles of these that are off cancel at those locations. All right, that's rule number 2. Let's look at rule number 3. This one is what I refer to as the asymptotic behavior of the, or asymptotic behavior for large values of gain k. And I'm going to assume if P represents the number of poles and Z represents the number of zeros, I'm going to assume that the poles and the zeros are not the same value. I have more poles than zeros. So D of S is going to be of higher order than N of S. And really what we're doing, we're not directly finding the root locus in this. We're finding guidelines. We're finding asymptotic sketch lines in rule number 3, and our root locus branches will approach those guidelines as k gets bigger. We are here finding asymptotic lines that help in the sketching of the root locus. And here are how we find those lines. The root locus is going to be asymptotic, or these branches of the root locus, to straight lines with angles given by the following formula. The angle, which we will say these asymptote angles, phi sub a, are equal to 2L plus 1 times 180 degrees, all divided by P minus Z. And L we let range between 0 up to P minus Z minus 1. If we have 4 poles, P is 4, and 2 0, well, let me say 1 0. 4 poles and 1 0. P is 4, Z is 1. The pole 0 excess, which I will refer to a lot, is 4 minus 1, or 3. We would then be dividing that numerator by 3, or effectively we're dividing 180 by 3, or 60 degrees, and we'll now have angles that are integer multiples of 60 degrees. That will determine where these lines are going. If you have lines, you now have to play the birthday game. You don't know where those lines are emanating from on the real line, and so it's not completely clear where to sketch those. So we need a centroid. Where do we pin those angles down? These straight lines will actually intersect at a point which we will call sigma sub a, the centroid, on the real axis, given by the following formula. Sigma sub a is now going to be the sum of the poles of G of S, H of S, minus, boy, I'm going to run out of room, but I have an infinitely wide, the zeros of G of S, H of S, all divided by the pole 0 excess. what in the world is sigma sub A? Sigma sub A, let's say you had a pole at -1 and a pole at -2 and a pole at -3. Then we sum those up. We sum -1, -2, and -3 to get -6. Then if we had a 0 at -1/2, we would subtract -1/2 from -6. So we would end up at -6 plus 1/2, which would be -5.5. And we would divide that by P minus Z. We'll start at that point on Friday.